Let ABC be an acute triangle with circumcircle omega. Let B0 be the midpoint of AC, and let C0 be the midpoint of AB. So these are the midpoints. Let D be the altitude from A, and let G be the centroid of the triangle ABC. And we construct a circle tangent to omega that passes through B0 and C0 and is tangent at a point X. And this is little omega, this is big omega. So let me go ahead and label that. And what we want to prove is that D, G, and X are collinear. They all lie on the same line. In order to solve this problem, we'll need to start by defining some theory called inversion, where we invert about the plane. So, inversion. So what is inversion? Well, consider you have a circle here, and then you have the center O, and then you have a point P here. And then the radius of the circle is R. Well, what is a point on the segment OP, let's call it P star, such that OP star times OP is equal to R squared. And P star is called the inverse of P with respect to the circle, because we're pretty much inverting the distance. OP star times OP is equal to R squared. So how does inversion actually help? Well, the key fact is, we're going to need a few key facts in order to solve this. And the main thing is, if you have a circle O here, and then you have an arbitrary line, let me go ahead and draw a better circle, and then you have an arbitrary line, then what happens if we invert all of these points? Then it turns out that if we invert all the points on this line, we end up getting a circle that passes another circle that instead passes through O. So how can we go ahead and prove this? So let's go ahead and draw another one here. So that's O. And then we have A here, or we can just go ahead and draw our line without that. So let me go ahead and draw it again. So O. And then we have this line here. And we want to find out what the set of points is, such that, so if the foot from O to this line is, suppose, X, then this is X star. Then we have another point Y on this line, and then we draw this, and then it intersects at a point Y star prime. What we want to show is that OY star prime times OY is equal to R squared, which is equal to OX star times OX. And in order to show this, it's actually equivalent to X star X Y Y star prime being cyclic. But since OX star is a diameter, because suppose we have this, we're claiming that this desired circle is a circle with diameter OX star. And that means that OY star prime X is equal to 90 degrees. And that means that this angle is 90 degrees. But this angle is also 90 degrees since X is a foot from O to the line, hence the quadrilateral cyclic, which means that OY star prime times Y is equal to R squared. So that proves that the inverse of a line is a circle passing through O, which is really interesting. It turns out that there's even a more general claim, that any two circles invert to each other with respect to another circle. And to prove this, we have points A and B here, such that OA and B are collinear. Then we construct the inverse of A, which is A star, and the inverse of B, which is B star. And we claim that the circles with diameter AB and A star B star invert to each other. And to see why, we pick a point D here, and we let D star be the inverse. And what we want to show is that if D star is the inverse, then B star, D star, A star is equal to 90 degrees. That's what we want to show. So how do we go about proving this? Well, we have this angle here, B star D star A, and we might want to split it up. So this ends up being B star D star A star is equal to angle B star D star D plus directed angle D star A star. Now we know that B star B D star is cyclic, since OD star times OD is equal to OB star times OB, which is R squared. So that means that this is B star BD plus, and similarly A star AD star is cyclic, so this is DA star. And then we now note that we have B star BD, which is just ABD, and then DAA star is just DAB. And by the sum of the angles in triangle ADB, this ends up just becoming ADB, which is 90 degrees, since D lies on the circle with diameter AB. And hence D star lies on the circle with diameter A star B star. Therefore, any two circles invert to each. A circle always inverts to another circle, sorry. So now that we know that, we can now start discussing an important concept that we're going to be looking at. And it's called a force overlaid inversion. So we have A, B, and C, and a triangle ABC. And what we're going to do now is take an inversion about a circle with radius square root AB times AC. Now, what does this do? Suppose this inverse here is B star, and this inverse here is C star. Then AB times AB star is just equal to R squared, which is AB times AC. So therefore, the AB's cancel out, so that means that AB star is equal to AC. This ends up meaning that AB star is equal to AC, so we can go ahead and make B star more accurate, as well as C star. So this should be C star. And given these lengths, we might be motivated to reflect the result of inversion about the angle bisector. So we have that, and then and that means that B and C end up going to themselves. So a force overlaid inversion is an inversion about A with center A with radius square root AB times AC, which is also commonly denoted as square root BC inversion, followed by a reflection across the angle bisector. So that's a force overlaid inversion. Let's take a look at what it does. So we have A, B, and C, and then we draw the circumcircle, for instance. And we now note that a force overlaid inversion, it maps B to C, and it maps B to itself and C to itself, but it doesn't map the segment BC to itself. Instead, it maps the segment BC to a circle passing through A. And since B and C must lie on this circle, the line, when we force overlay, the segment BC and the circumcircle of ABC invert to each other, which is really interesting. So that's the one property that will need to solve this problem. And one final note, inversion preserves a lot of nice things, like things that are preserved are tangencies, and then there are things, and that's the main thing that we're going to, that inversions preserve tangencies. and like the pairwise relationship, I should say, between circles. With that said, let's go ahead and get to solving the problem. So here we are back at the problem, and recall the problem. You can pause the video for a second to reread it. So how do we deal with this tangent circles? Like, how do we construct it? Well, we might want to just look at the line DG for the time being. So let's go ahead and erase these guys. And then let me go ahead and draw this stuff back in. And then this ends up being B0. And we can erase this point X because we do not know which point X it is. We want to work backwards. So we end up constructing this. So we end up constructing this line here. Let me go ahead and reorient it. There we go. And then the two intersection points with DG and the circumcircle end up being this point X prime and then X. And we want to show that one of the points X of intersection ends up being the one where B0, C0, X is tangent to the circumcircle. But this point X prime might seem particularly interesting because it seems like that AX prime is parallel to BC. That's a conjecture. So let's go ahead and ignore X prime, normal X for the time being, and show that DG and X prime are collinear, where X prime is a point such that AX is parallel to BC. Well, given a centroid, it always motivates us to construct a medial triangle. Whenever we have a centroid, always construct a medial triangle and see what happens if we take a homosity of scale -2, sending the medial triangle to ABC. And we want to show that the point D gets mapped to the point X prime ideally. In other words, since ABCX prime is an isosceles trapezoid, we want to show that B0, A0, D0, C0 is an isosceles trapezoid, or that B0, A0, D, C0 is cyclic. But recall my video on the 9-point circle, which states that these points are concyclic, as well as the other feet of the altitudes. So that means that DG and X prime are collinear. So that means that we can entirely get rid of the centroid from the problem and just rephrase everything in terms of just D and X0, and we don't even need to worry about the centroid. So let dx prime intersect at x, and we let C0 and B0 be the midpoints. And now we'd like to show that C0, B0, X is tangent to the circumcircle. So how can we go about get started on this problem? Well, we have these tangent circles and stuff like that. So this motivates us to take an inversion. More specifically, we might want to think of force-related inversions because we have a lot of these points here, and that's the only really nice inversion that involves that more lean towards A. So let's try taking a force-related inversion. So let's take each one thing one step at a time. The line AD, it inverts to the line AA prime, where AA prime is a diameter, because it's pretty easy to show that this angle and this angle are equal, and hence these lines invert to each other. Because the inverse of a line passing through A is just itself. And then when we reflect it across the angle bisector, these angles must be equal, and hence we have the AA prime. Moreover, the segment BC inverts to the circumcircle of ABC, which makes the point D maps to the point A prime. So I'll go ahead and put that in red, A prime. So D's out of the way. Now what about x prime? So for the point x prime, we have that ax prime is parallel to BC. And when we reflect the point, we end up getting something like that. And then we want to see when it intersects with BC. So AX prime is parallel to BC, which means they don't intersect. And this means that the mapping of AX prime should only intersect the mapping of BC, which is the circumcircle of ABC, only once. Once and only once. Which means that this is a tangent. So go ahead and call this point here Y. And so let me go ahead and see what we know so far. So D gets mapped to A prime, and X prime gets mapped to Y. And now let's go ahead and figure out where X goes, such that B0, C0, X is tangent to this circumcircle. If we take a force overlaid inversion, then we have this here, and then this here. Sorry for different colors. Then the point C0 gets inverted to the point here, C0 prime. Initially, the point, like, it gets mapped to this one because AB0 times AC0 prime, AC0 star, and I forgot to specify that C0 star B is equal to BA. Then AB0 times AC0 star is equal to AC over 2, since AB is half of it, times 2 times AB. And the two halves cancel out, and we get AB times AC. So hence, C0 inverts to the reflection of A across B, C0 star, and then the B0 gets mapped to the reflection across C of A, so B0 star. And now we want the we want to point X star on BC, such that C star, B star, C0 star, B0 star, X star is tangent to the segment BC. So let's go ahead and draw that in. Something like that. And we now know that in order for this to happen, X star must lie on the perpendicular bisector of C0 star, B0 star. So that ends up being really nice for us. So let's go ahead and get rid of those. And we now just construct a perpendicular bisector. And then it intersects at a point, suppose X star. Now at this point, we know that the perpendicular from A to BC is D. The perpendicular from the point M, like the perpendicular bisector, is M. So if we take a homothency of scale 2, we end up getting that the perpendicular bisector point, we can get rid of B0 star and all of this stuff here. It ends up being, if this point M is a midpoint, the reflection of D across M. So D star. Or I should call it D prime. And what we wish to show, since we want to show that dx, x star are collinear, if we got rid of the point x in the picture, we can end up erasing all of this stuff to make things not a mess anymore. So let's go ahead and clean things up. So the C0 is not needed anymore. And then we let D be the foot of the altitude, M is a midpoint, D star is a reflection, and then A prime is an antipode, the point diametrically across. And what we want to show now is that A prime, D prime is cyclic. We've reduced it to this by force overlaying. So how can we go about proving this? Well, this should kind of be obvious because it turns out it has diameter a star a prime y, and this is because the angle a prime dy is equal to 90 degrees. And this is by the reflecting the orthocenter lemma, if we recall that. However, we know that the directed angle a star ay is equal to 90 degrees because ya is tangent, and we're done. So, and this is one of the many examples that get trivialized by inversion. But the main effort is required in determining what happens when you invert. And if you want to see another really wonderful example of inversion, my friend Mop2024 has a video related to it. And it's an AIME problem that ends up being trivialized by force overlay inversion. It's a problem 15. And so I highly suggest you check out his video. And in general, if you like his video, then please go subscribe to him. He's a really good friend of mine, has awesome videos, guaranteed. So thank you so much for watching. I hope you enjoy. Please subscribe to my channel and his channel as well.